The last thing I want to point out is that if the variance of my x values was equal to 1, and if the variance of my y values was also equal to 1, then this slope estimate is the same as the correlation that I would calculate based on this data set. And we often refer to correlation as R, little r. Okay? So if the sample variance of the x's is equal to 1, and the sample variance of the y, this is a comma, and the sample variance of the y's is equal to 1, then my estimate of the slope is just the correlation. Slope is just correlation. Slope is correlation standardized, because typically our sample variances of x and y are not exactly equal to 1. So if this statement right here is not true, my slope is equal to the correlation times the ratio of the two standard deviations. This quantity here you can think of as just making sure that our slope is in the right units. If our y value, if our outcome is heights, this sy makes sure that we know whether we have inches or centimeters. If we change from inches or centimeters, if we change from inches to centimeters, we could change this sy. Suppose the x's are weights and we want to go from pounds to kilograms, the sx makes sure that we do that. So slope is just correlation standardized to have the right units. So another way to think about this is, suppose I started out by representing my x's and my y's in terms of standard deviations so that they both have variance 1. Suppose I standardize my data set. Suppose I standardize my data set so that the variance of the x's is 1 and the variance of the y's is 1. Then I calculate the correlation, and that is just the slope. And now I say, okay, but actually I need to multiply all the x's by 3 because I had divided them by 3 to standardize. All right? Then I should divide this slope by 3. Suppose that if I want to unstandardize, I need to multiply all my y's by 2. Great, multiply by 2. It's just putting the slope on the same scale as the correlation. Remember that correlation doesn't have a scale. Correlations are always between -1 and 1, regardless of whether you're talking about inches or centimeters. If I measure height in inches and calculate a correlation, and then measure it again in centimeters and calculate a correlation, the correlation won't change. Correlation does not have to do with what scale you use. But slope does have to do with what scale you use, because slope says how much should y increase for every unit x increases. And so if x is equal to an inch rather than a centimeter, or a pound rather than a kilogram, the slope is influenced by that. Slope is just correlation, standardized. And if I were to write down the expression for correlation and the expressions for standard deviation, we could show that this quantity is just the standardized slope. This all works out mathematically as well. So again, all we're trying to do is find the line that kind of goes through these points. And we could make lots of different arguments for how to do that. The regression line that's conventional is just one way to do that. This is just one possible estimate of the slope. But it's conventional and desirable for several reasons. It minimizes the sum of the squares residuals. It leads to an unbiased estimate of the true slope. In other words, if I were to repeatedly sample from the model implied by this line and estimate beta 1 this way, on average I'd get the right answer. It's a maximum likelihood estimate. It's the estimate that maximizes the chances of seeing this data set. It's the weighted average of the slopes. If I calculate the slope between each point and the middle and take a weighted average of those, where the points further out in terms of x get more weight, I'd get the same value. And slope is just the correlation between x and y, but standardized to have the correct